So good afternoon and welcome to this lesson dedicated to mechanical properties of materials, which is given in the frame of the class Materials and Their Properties at the Federal University of ABC. So in this class, we are going to discuss the importance to determine mechanical properties of a material to design a structure, to know how to perform a tensile test and which information can be extracted from the results. We are going to describe the elastic behavior and plastic behavior and understand what happens at microscopic scale and what is observed at the macroscopic scale. And then we will understand and compare the mechanical behaviors of metals, ceramics, and polymers. And finally, we will introduce hardness. So in this slide, you can see various examples that illustrate how it is important to know the mechanical properties of a material, or either to select an appropriate material for a specific application where in which we know what will be the load that will be applied on the material, on the structure. So in the first case, you can clearly see that this plastic chair is failing to withstand the weight of the person that is sit on it. So in that case, you have a deformation of the chair. On the second case, it is an application, it is different pieces in a motor. In that case, you will have the rotation of these different pieces that will be in contact one with another. And in that case, you need to have high resistance to abrasion of the surface of these different pieces. In the next case, it is an accident that occurred on North Brazil on a bridge that you can see that the middle of the bridge falls down during the day. So in that case, a bridge is working some part under compression, under tension, and also is subjected to vibration when the car passes on it. And in that case, the structure was not well designed and totally failed. The next case is a case of a dental implant made of ceramic. In that case, you should imagine that this implant will be submitted to cycles of repetitive loading during chewing food. And so it should be able to maintain its mechanical resistance and its integrity during years. And so various cycles of compression. The next case is a plastic bag. So in that case, it's more simple. It should withstand the weight of the different things that are carried on. On the middle of the slide, you can see a structure. In that case, the goal of such a structure, on which you can see that you have many holes that are a different orientation, is to be lightweight, but also to have different mechanical properties on different directions. So on the horizontal direction, you are looking for flexibility of this structure, whereas on the direction that is perpendicular to the slide, it should be mechanically resistant. And so you can see that in that case, it's a combination of the material, in that case, it is a polymer, and the structure built for the product. And the final example that is shown is a glass that is fragile. So in that case, it should show that this kind of material are break under high stress. So now we are going to introduce some mechanical properties. So in fact, there is a variety, there is various mechanical properties such as tensile resistance, stiffness, ductility, impact resistance, creep resistance, fatigue resistance, hardness, toughness, and so on. So depending on the application, on the product that we want to build, we should identify what should be the mechanical properties that are important for that case. But in every case, All these properties are related to the ability of the material to resist and or to transmit the mechanical load. And this mechanical load can be either static or dynamic. And so we should understand if submitted to a specific mechanical load, if the product will be deformed permanently, or if it can recover its shape after we remove the mechanical load, either if it will break. And so that's why it is important to understand these mechanical properties. And the mechanical properties are related to the material structure, so the chemical bonds, the crystalline structures, the defect, and so on. So when we talk about mechanical properties, it is important to introduce stress and strain. So the mechanical properties describe the behavior of the material under mechanical loading or stress. So we are going to see the relationship between loading and stress. So the stimulus that is applied on the material is a specific load that we define, and the response that is registered is a strain. Or the contrary, we apply a specific strain or deformation, and we record the load. So the stress can be of 4 kinds, 3 in fact, because the last one, torsional stress, is a specific case of shear. So the 3 stresses are tension, compression, and shear. So let's see the first one, tension. So here in dashed line is the original specimen on which we apply a specific load here. And in that case, this load is applied on the 2 surfaces, top and bottom of the specimen. It is an uniaxial stress since we apply this force only on one direction. And so applying this stress, we are going to see that the length of the specimen is going to increase and the diameter of the specimen will decrease. And so the stress, sigma, is equal to the load that is applied on the 2 surfaces divided by the cross-sectional area. And you can see that the area is taken as the initial cross-sectional area. So the area of the initial specimen. So the load is in Newton, the area is in millimeter cubic, and so the stress is in megapascal. So it is the same unit as the pressure. In compression, so in that case, a compressive force is applied to the specimen, and the direction of the force is in the opposite direction to tensile stress. So we are going to see a decrease of the length of the specimen and an increase of the diameter. In the case of shear, so it is a little bit different than tension and compression, because in these 2 cases, so the force was applied perpendicularly to the surface of the specimen, whereas the shear force is tangential and applied on the top and bottom surfaces. So the vector force is parallel to the surface of the specimen. And in that case, we define the deformation as the tangent of this angle theta. And finally, torsional stress. It is a variant of shear. We produce, in fact, the twisting of the specimen due to an applied torque applied on one surface of the specimen. So this, the bottom surface, does not move, whereas the top surfaces, on the top surface, we apply a shear stress. And so in the shear stress, you can see that the definition, calculation of the shear stress is similar to the one that we described for tension and compression. So it is the load divided by the cross-sectional area of the specimen. And so the mechanical properties, they will depend on the nature of the applied load. So if it is dynamic or if it is static, depending on the kind of stress as we described. Its duration, so it is not the same case if the stress is applied just instantaneously or for a very long period. Depend also on the environmental conditions, such as the temperature, the climatic conditions. So previously in that class, we saw an illustration of a case where the temperature was very important. And so if you remember, we were talking about this O-ring that was used in this shuttle. And this O-ring made of elastomer, at the temperature of the day it was used, on the day of the shuttle landing, so this polymer was rigid, whereas normally on the condition it was designed to be used, it was much more elastic. And so depending on the temperature, the behavior of this material is different, was different, and so that's why the mechanical properties here is an illustration of the fact that the mechanical properties of a material depends on the temperature. And so it also depends on the magnitude of the load, and as I said, either it can be constant with time, either it can fluctuate. So how to measure a mechanical property of a material? So first of all, you should select the mechanical test to be performed, and this depends on the kind of material you are working with. So for example, if it's a ceramic, as we will introduce in this lesson, we will prefer to perform a flexure test instead of a tensile test. But the selection of the mechanical test should also depend on the condition or the mechanical load that this material should withstand during its use. So it may depend also on the application you are looking for this material. Then you should prepare a specimen of your material of a determined size and shape. So here is an example of, on this figure, of a specimen. And so you can see that the shape is very specific. You have on the two sides, you have a grip section. So the width of this grip section is wider than the middle of this specimen, because it is the place where we will grip this specimen in order then to perform the tensile test, for example. So the machine will be in contact with the specimen on these two parts. Whereas on the middle of the specimen, you have the gauge length, where in fact the load will be applied. And so depending on the material you are working with, the size and shape of the specimen is specific. And as you can see, you have standardized testing techniques. And so this standardized condition and dimension of the specimen are specified in this kind of document. And then you should select the appropriate conditions in which the test must be performed. So for example, it is important to determine what is the strain rate. So, or if the test should be performed in presence of humidity or temperature and so on. So the size of the specimen and the appropriate conditions, as I said, are given by standardized testing techniques. And for example, if you want to see this information for performing a tensile test of metallic material, you should refer to this standard. So ASTM, which means it is a standard of the American Society for Testing in Materials. And so you will find all this information. And so it is important to follow the technical standards because it enables you to obtain results that you will be able to compare with the literature and with other data. And sometimes it's very important if you want to register your material or your product for a specific application. And so depending on the country you are working in, for example, here in Brazil, you have the Associação Brasileira de Normas Técnicas, but in different countries, you will have different specific technical standards. You have ISO and ASTM that are more that are used worldwide, and so you can find information about how to measure mechanical property of a material in this kind of document. So we will define what is a mechanical test to be performed. We will define the size and shape of specimen and the conditions to perform the test. And then we will be able to describe the mechanical behavior as three parts. We will have the elasticity, plasticity, and fracture. And so fracture is very easy to understand. It is when the material breaks. But let's focus on elasticity and plasticity. So the deformation can be elastic or plastic. So let's define these two deformations. So the elastic deformation is not permanent. So I apply a load on my material, and when I release this applied load, the material returns to its original shape. So it is, for example, the case of elastomers. So in that case, we say that elastic deformations are reversible. On the contrary, the plastic deformations are permanent. So they remain when the applied stress or applied force is withdrawn. So it is not recoverable due to permanent atomic displacement. So elastic deformation is reversible. Plastic deformation means the material is permanently deformed. So in that class, we will describe the tensile test, which is the most common test to measure mechanical properties of materials. So we are going to see how is it performed. So in that case, we will have prepared a specimen following the technical standards for the dimension and shape. And so this specimen will be deformed with a gradually increasing tensile load that is applied uniaxially. So do you remember that when we are talking about tensile load, we are talking about tension. So in that case, we will apply the load on one axis. So in that mechanical test, the stimulus will be elongation or strain at a constant rate. So, for example, 5 millimeters per minute. And the response that will be recorded will be the load to produce this specific elongation. So here is a schematic representation of the apparatus that is used to perform this tensile test. Here you can see the specimen, which is held by two grips. So the bottom holding grips is attached to a stationary base, so it doesn't move, whereas the upper holding grip is attached to this part of the apparatus that is going to move. So in this test, as we said, we will control the strain rate, and you will have this load cell that will continuously measure the applied load that needs to be applied in order to deform, in order to maintain this elongation rate. And so in order to measure with more precision the elongation of the specimen, we can also use what we call an extensometer, which is an apparatus that will measure the deformation of the specimen on its gauge section. So from this tensile test, we will obtain such kind of results. So as you can see, there is a stress represented as a function of the strain. So the stress, also called engineering stress in that case, is the load divided by the initial cross-section of the specimen. So let's remember here you have a representation of the specimen before deformation and after being deformed. And so we will take into account the initial cross-section of the specimen to calculate this engineering stress. And so let's remember that in that case, we record the force necessary to get a deformation of the material. Okay, and so the strain, how is it calculated? So the strain is the variation of the length of the specimen at any point divided by the initial length of the specimen. So as you can see, since it is a length divided by a length, so the strain is dimensionless. So it is very important to remember this. And very often we will express it in percentage. So it is this expression, this equation multiplied by 100. And so along the test, we will observe a change of the dimension, of course, of the specimen, so it will elongate, but also we will observe a change of the shape. So as you can see, as it is represented in that case, you have a cylinder that become to transform into something that have a necking. So there is a constriction or the diameter that is reduced on a point, a specific place on the specimen. And we are going to describe what are the information we can get from these results and what is happening in the material and in the different kind of material when we perform this test and at the different point of the curve. So here is the same or another stress strain curve, and we can distinguish two regions in that curve. First of all, you can see that there is a first region when we begin to apply a load, tensile load on the material. There is a first region where we have a linearity between the stress and the strain of the material. So in this region, we have elastic deformation. So let's remember, we have a recoverable deformation. And then up to a point, there is no linearity, no more linearity between the stress and the strain. So this is the second region in green. So this is a region of plastic deformation. And so the deformation produced up to this strain is permanent. So we are going to describe, first of all, elastic domain. So this is this blue region. And then the plastic regime, which is this green region. So first of all, let's talk about elastic deformation. So as we said, it is reversible, which means when the applied load is removed, the sample recovers its initial dimensions. So we have linearity between the stress and the strain, and this is represented, or this is expressed by the Hooke's law, which is a constitutive equation, which means that all the material will respect this law in their elastic regime, in the region of the stress strain curve that represent elastic deformation. And so this equation introduces this modulus E, which is a modulus of elasticity that we also call Young modulus. So in fact, when we use this curve, this elastic modulus is the slope of the curve, and so we can easily calculate it using the experimental data. Okay, so let's remember again. So this elastic deformation occurs at low strain or low stress, and so if I apply a load to my material in this region and I remove this load, it will come back following the same curve to the initial state, initial dimensions. Okay? So this elastic modulus may be thought of such as the stiffness of the material. So it is the material resistance to elastic deformation. So depending on the value of this Young modulus or modulus of elasticity, depending on the shape of this curve, so if it is more vertical or more horizontal, it will give an idea, or it will represent, in fact, the material resistance to elastic deformation. So the lower the elastic modulus and the lower the material resistance to elastic deformation, the lower the stiffness. Okay. On the contrary, the higher the modulus of elasticity and the higher the stiffness. Which means I must apply a higher stress in order to obtain the same deformation to my material if its elastic modulus is higher. And so you can see here on this table that depending on the class of material, the range of value for the modulus of elasticity is quite different. So for metals, it will range from 45 to 400 gigapascal. For ceramics, 60 to 500 gigapascal. And for polymers, these values are much lower, so from 3 megapascal to 4 gigapascal. So let's understand what is happening at the atomic scale in order to explain the elastic deformation. So in this regime, we have small changes of the interatomic distance or stretching of interatomic bonds when we apply the stress. So there is no breaking of bonds, there is only increasing of the distance between two atoms. And in fact, the elastic modulus is proportional to the derivation of the interatomic force in function of the separation of the interatomic distance between two atoms at the distance corresponding to the equilibrium distance between two atoms. And so if you remember at the beginning of this class, we introduced such graphic that represent the force as a function of the separation distance between two atoms. And so we determined that the interatomic distance, which is the distance of equilibrium between two atoms, is found when the value of the force is equal to 0. And so here we are saying that the elastic modulus is proportional to the tangent of such a curve at this distance of equilibrium. And so, for example, if I represent the evolution of the force as a function of separation of two materials, as you can see on this graph, I will be able to say that the material that will have the higher elastic modulus will be the one that has the tangent with the highest slope at the interatomic distance of equilibrium. Okay, so in fact, in this region of elastic deformation, the elastic modulus will measure the resistance to separation of adjacent atoms or ions or molecule, and it is directly related to bonding force. And so the materials that will have high bonding force between the atoms will have higher elastic modulus than the one with a low bonding force. And so this is directly related to what we studied at the beginning of the class when we describe the force of the atomic bond that we find in each class of material. And so just remember, in order to present the difference between elastic deformation and plastic deformation, here we do not have breaking of the bond during stretching, only increasing the distance between the atoms. And so in the literature, you will find such kind of graphics that represent the value of the elastic modulus for different classes of materials. And so you can see that in metal or in ceramic, you will have value of elastic modulus that will be higher than for polymers. And if we prepare a composite or using fibers, we are going to be able to change a little bit the value of the elastic modulus of a material. So for example, if we prepare a polymer in which we have fibers of glass fibers, for example, there is an increase of the elastic modulus of the material. Okay, so this range of value of elastic modulus, as we said, is directly related to the force of bonding between atoms in this material. So when we performed the tensile stress, we applied a load in the direction, so let's say in the direction Z. And considering that the volume of a material is almost constant, we will observe a constriction in the lateral direction, x and epsilon. And so we can define a compressive strains that occur in these two directions, so epsilon x and epsilon y. And if the material is isotropic, which means it has the same composition and the same kind of bond in all the directions, so we will have the compressive strains epsilon x that is equal to the one in epsilon y. And so we will define the Poisson's ratio as minus the compressive strain in the transversal direction divided by the one, the tensile strain in the actual direction, so in the direction in which the load is applied. And so, for example, considering an isotropic material, it will be equal to minus epsilon x divided by epsilon z. And so, depending on the class of material, we will have different range of value for this Poisson's ratio. So if we have a material for which the volume, the variation of the volume is equal to 0, the Poisson's ratio will be equal to 0.5. If the variation of volume is higher than 0, so the Poisson's ratio will be lower than 0.5. And so for many metals and alloy, this Poisson's ratio will be approximately equal to 0.3, whereas elastomers have a Poisson's ratio above 0.5 because there is no volume change during stretching of such material. So this value will give us an idea of what is going to happen in the different direction of the specimen when it will be under tensile load. So this is very important when we are thinking about designing a structure in order to know what is going to happen in all the dimensions of the product. So talking about the elastic properties, we are describing it for a tensile test. But as we said, we can also apply a shear stress on the material. And so in that case, we are talking about shear test, and we can make some correlations with the tensile test for the elastic region. And so let's remember, in a shear test, here we have the specimen, and we apply a force in the same plane as the surface of this specimen, and we observe the deformation with the variation of this angle, theta. And so the stress, the notation for the stress in tensile test and shear test is different. In the case of the shear stress, the strain is equal to the tangent of this angle, theta. And we have also a constitutive equation that presents a relationship, the linear relationship between the stress and the strain. So in that case, we have this parameter of proportionality, which is called the shear modulus. So in the case of the tensile test, we have elastic modulus, and in the case of the shear test, we have the shear modulus, which is G. And there is a relationship between the elastic modulus and the shear modulus, and here you can recognize this parameter, which is Poisson's ratio. So we describe what is happening in the elastic region. So we have linearity between the stress and the strain, and it is recoverable deformation. Now let's introduce the region of plastic deformation, which is here represented in green. So there is a transition from the elastic deformation domain to plastic deformation, which occurs at a certain percentage of strain. So first of all, we apply a load on the specimen. It is elastically deformed, so there is a stretching of this interatomic bond. And then up to a certain percentage of strain begins the plastic deformation. So in this plastic regime, the stress and strain are not anymore proportional. So the plastic deformation means the deformation is permanent. And here we have the breaking of bonds between two neighbor atoms. And along the stretching of this material, these atoms will form new bonds with new neighboring atoms after motion. After removal of the stress, the atoms do not return to their original position. And so there are different mechanisms that can explain this plastic deformation in crystalline and amorphous materials. And so we are going to describe this mechanism. So this transition from the elastic domain to plastic domain is determined by this point, P, which is a proportional limit. So it is a point at which deviation from linearity is first observed. But it is not very easy to determine this point P. And so what do we do practically? In fact, we will define the yield point, which corresponds to the stress necessary to promote a permanent strain of n%. So what are we going to do? Depending on the class of material you are working with, so metal or ceramic or polymer, you will find this value, the value of n, in the literature. So for metals and alloys, it will be 0.2%. For ceramics, 0.1%, and polymer 0.5%. And so you will, here on the graphic, you will you will determine this n%, this strain, and you will draw a straight line parallel to the elastic region, and the cross-sectional point between this straight line and the tensile curve will be the yield point. And so this yield point will be more practical and will be used practically to determine the transition from the elastic deformation to plastic deformation. And so the magnitude of the yield stress is a measure of the material's resistance to plastic deformation. So in some material, we have a specific phenomenon for the yield point. In some metals like steel, we have a very well-defined elastic plastic deformation. So here you can see the elastic region, and you observe after this point, the upper yield point, a decrease of the stress, which means there is a release of stress. And in this range of strain, the stress to provoke such deformation remains the same. And so in that case, we will define the yield stress as the average stress that is associated with the lower yield point. And so you don't need to apply the strain offset method that we described in the previous slide. So now, once the material enters in the plastic regime, so approximately at this point right here, so the stress necessary to deform this material apparently will continue to rise up to a specific point, which is the point written M, which corresponds to the maximum stress that can be sustained by a structure in tension. And so we will define this value, the stress at this point, as the ultimate tensile strength, so which is written sigma UTS, which is the stress at the maximum of the stress strain curve. And so in metals, typically, the value for the ultimate tensile strength is between 50 to 3000 megapascal. And after this ultimate tensile stress, we have a decrease, apparently on this curve, we have a decrease of the stress up to a point where the material will break. And so in order to describe the point at which the material breaks, we define the stress and deformation at break. So the stress is written on the y-axis, while the strain at break is determined on the x-axis. So after having performed a tensile test, we can define other properties by using the results, so using the stress-strain curve. And the first property is ductility. So ductility measures the degree of plastic deformation sustained at fracture. So on this graph, you can see two very different behavior. You can see the first material is not highly plastically deformed. You can see that it's break at a relatively low strain after the elastic domain. So in that case, we will say that this material is brittle. It experiences little plastic deformation upon fracture. On the contrary, we have a ductile material. So a ductile material is a material that experiences a higher plastic deformation upon fracture. So you can see that in that case, the strain at fracture is high. And you can notice some differences between the behavior or the other property of a brittle and ductile material, is that for materials that generally have a high elastic modulus and a stress at fracture that is quite close to, or yes, close to the yield point. So the material has a brittle behavior. On in the case of ductile materials, you have generally elastic modulus that is lower, and the yield point of ductile materials generally is lower than the one of brittle materials. And so this behavior is related to the chemical bonds and the structure of this material. Then we can define toughness, which measures the ability of the material to absorb energy up to fracture. So it is defined as the area under the stress-strain curve. So the unit of the toughness is Joule per meter cubic. So it is energy per volume. And so a material to be tough must display both strength and ductility. So in that case, you can see that in the case of the ductile material that is represented on this graph, the toughness, its toughness is higher than the one of this brittle material. And so in some application, like in that case, in a car, the front part should not be brittle. It should be ductile and have a high strength. So it should have a high toughness in order to absorb energy, a high energy, up to fracture. And so you can see that in that case, it is plastically deformed. And so we say that in this application, we needed a tough material. So finally, we can define the resilience, which measures the ability of the material to absorb energy when it is deformed elastically, and then upon a loading to have this energy recovered. So it should be like a little bit a spring. We deform it elastically when we compress it. It absorbs energy, and it is able to recover this energy when we release the compression load applied on this spring. And so the resilience, in the same way as the toughness, we define it as the area under the curve. So let's remember, in the case of toughness, we were considering the area under the curve of the elastic and plastic domains, whereas in the case of resilience, we are only focusing on the elastic domain. And so in order to measure this resilience, we use the modulus of resilience, but it is basically the area under the curve. And so resilient material will be the one that have a high yield strength. And for two materials that have the same yield strength, the one with the lower elastic modulus will be the one the most resilient. So now let's talk a little bit about the comparison between the true stress and engineering stress. So up to now, we were talking about engineering stress that we defined as the load divided by the initial area of the specimen, so the area of the surface on which we apply the load. And if we look back to this graph, we can see that after the point M, it seems that there is a change of the shape of the specimen. In fact, after the point M, we don't observe anymore a cylindrical shape, as it was the case before the point M, but we observe a kind of formation of a neck on the specimen at a specific point of the length of the specimen. And due to necking, there is a change of the shape and a dramatic change of the cross-section. And so it seems, when we represent the engineering stress, it seems that beyond this point M, the stress is decreasing up to fracture, but it is not the case. We are continuing to increase the stress, but since due to necking, there is a reduction of the cross-section of the material, of the specimen, and so in fact the stress increases, and so we call it the true stress. So we make the difference between engineering stress that seems to decrease after point M and the true stress. So let's define the true stress. So it accounts for the normalizing. So it normalizes the instantaneous load with the instantaneous cross-sectional area of the specimen. So it is the instantaneous load divided by the instantaneous cross-sectional area. So at any point on the graph, at any strain, we define this value for the stress. And in fact, the strain can be written as a logarithm of the length of the specimen at this specific strain, divided by the length, the initial length of the specimen. And so here on this graph, you can see a comparison of what is the representation of the engineering stress. So it is similar to the curve we already discussed. And what is the true stress that we observe considering the reduction or the change of the cross-sectional area of the specimen at any time. And so you can see that in fact the stress is increasing in the specimen even after point M, so even after the necking phenomenon. So up to now, all the stress-strain curves that we studied are typical of metals. And let's see what is going to happen in a metal when we applied a tensile load to the material up to reaching the plastic deformation if we release the load. So let's stretch the sample up to this point D. We could expect that the remaining strain of the sample would correspond to the coordinate on the x-axis, but in fact what we will observe is that this sample will follow here this unloading curve that is almost parallel to the elastic regime of this sample. And so the slope of this unloading curve is about, it is the elastic modulus. And so the difference in strain between this real strain after removing the load and the one that we expected is the elastic strain recovery. So it is due to the fact that even in its plastic deformation, the sample has elastic strain, and so it can recover it. At this point, if we apply again a load on the sample will follow this straight line up to point D. And then what we are going to observe is that there is a new yield point. So the yield point at the beginning of the stretching of the sample is represented right here. It is epsilon 0. And in the second case, when we stop the plastic deformation removes the load and reapplies the load again, there is a new yield stress that corresponds to epsilon E, right here, epsilon I. And so what does it say? It says that, in fact, in order to enter again in the plastic regime, the load to be applied to the material is higher than the initial load that was necessary, or initial stress that was necessary for the sample to enter into the plastic regime. So in fact, this, in other words, I can say that when the material is stressed again, the yield strength increases, and this is due to a specific phenomena that we encounter in metal, that is stress hardening. So let's explain what is stress hardening. So if you remember, in the lesson 5, we explained that there is a specific mechanism of plastic deformation in metals, which are due to the dislocation movement. So we explained that we have linear defects that are called dislocation that can move in the sample when we apply a load. So I just corrected right here. We saw this dislocation in the 7th lesson. So let's remember, we presented that we have two kinds of dislocation. We have edge dislocation and screw dislocation. And these dislocations are able to move in the material. And this enable us to explain plastic deformation. So when we apply stress on a crystal having this defect, the dislocation area moves. So bonds are broken and new ones are formed. So this screw dislocation or edge dislocation, the movement is different, moves in different direction in relation to the stress. And so this movement does not occur in any direction or in any planes. We explained that for a particular crystal system, for a particular metal, there are slip planes, which are the planes of the more dense atomic packing, so highest planar density, and the slip direction to the movement of this dislocation correspond to the direction in this plane, in this slip plane, that is the direction that has the highest linear density. And so we define that considering both the plane, the slip plane, and the slip direction, we have a slip system. And so this dislocation will occur in this slip system. And so in metals, we have quite a lot of this slip system, and depending of and this depends on the crystal system of this metal. But so we will have this movement of this dislocation that will occur in the plastic regime, and we will observe different movements for this dislocation. So in monocrystalline systems, it's quite easy to determine the direction and the movement of this dislocation, and they will occur within a single system. So the dislocation will cross all these single crystals. In polycrystalline systems, so we have various grains, and the dislocation will move within the grains up to reach the grain boundary. And in order then to be able to move this dislocation through the grain boundary, it will require a high load. And so I don't know if you remember, but in the 7th lesson, we also presented that this dislocation will move, and they will encounter one with another, and it will make it more difficult for them to move again. So it will require a higher energy, or I can also say it will require a higher load to make them move. And so this is the strain hardening phenomenon that explain why the, so I will come back here, it explains why once the metal has been stretched in the plastic regime, when we stretch it again, so we created dislocation. These dislocations are numerous, they are more difficult to move again. So that's why the yield strength to reach the plastic deformation domain, to be able to deform again this metal, is higher. So this is stress hardening, which is very characteristic to metallic materials. Now let's talk about ceramics. So here are represented the stress strain curve for ceramics, and you can see that this cross here represents fracture. So in fact, in ceramic, it seems that we only have elastic domain. So generally, we will say that ceramics have very little plastic deformation. And so once it will reach almost the end of the elastic regime, it will break. And so they will deform in a very low extent. So the strain at break is very low compared to metals and polymers. But the tensile test of ceramics present difficulties because it is more difficult to prepare specimen having the required geometry that is given by the technical standards. It is difficult to grip this brittle material because when we will grip it between the two grips of the tensile machine, the risk is to break it. And so even before beginning the test, the material will break. So very difficult to handle it. And ceramics fracture at strain lower than 0.1%. So this makes it very difficult to align this specimen between the grips, as I said, without breaking it. So these three factors make this tensile test difficult for ceramics. So that's why generally we don't perform tensile tests for ceramics, but we will perform a test that will give us equivalent information. So we will perform bending test or compression test. So let's see how does it work. This test is also called flexure test. So as you can see, in that case, we will prepare a kind of bar of ceramic, and we will perform a 3-point flexure test. So 3 points because we have 1 and 2 points for supporting this ceramic bar, and the third point is the one at which we will apply a pressure, a load. So in that case, this load will be from the top to the bottom, so it was directed to the down. And this force is applied at the middle, the equivalent distance between these two supports. Okay, and so either the bar is rectangular, either it is circular, and in that case, we will have the sample that will be different regions of the sample will be under different stress. So in the top region, so right below the force is applied, we have a region which is under compression, whereas the one that is on the bottom of the specimen right here, it is submitted to tension. So all this face, the bottom face is under tension, and the one, the upper one, is under compression. And so the result that we will have is that under this load, this part, the bottom part will break, and so we will be able to determine the flexural strength, which is the stress at fracture. So this stress at fracture, in fact, depends on three things. So it will depend on the specimen thickness, which is represented here by this parameter C. It depends on the bending moment, M, and also on the moment of inertia of the cross-section, E. And so here in this formula, to calculate the stress at fracture, we have the computation of these three information. So from the flexure test for ceramics, we are able to obtain equivalent information that would be obtained with a tensile test. We can see the elastic regime, which is represented by linearity between stress and strain, as you can see on this graphic. And from the slope of this curve, we can determine the elastic modulus. And for ceramics, the elastic modulus is range between 70 to 500 gigapascal, so it is slightly higher than the one of metals. And as we already commented, the ceramics are brittle, and so they break at low strain, and they are almost, so in that case they are not plastically deformed, but they can be when they are plastically deformed, they are slightly plastically deformed. Okay, so let's explain why ceramics are brittle. So let's consider first crystalline ceramics. So as in metals, the plastic deformation occurs via dislocation motion. So we define two kinds of ceramics, so ionic ceramics and covalent ceramics. So let's start with ionic ceramics. So in ionic ceramics, we have few slip systems along which dislocations can move. And this is due to the fact that we have cation and anions that are electrically charged. And so during the movement of a slip, a dislocation, we will have cation and cation that will become neighbors, and an ion that will become neighbor. And this is not favorable because we have an electrostatic repulsion between these charged species, which makes this movement of which makes the number of slip systems really limited in ionic ceramics. So let's remember, in metals, we do not have charged atoms. We have neutral atoms. So that's why the number of slip systems in metals are much higher than in ionic ceramics. Now let's consider covalent ceramics. So in covalent ceramics, we have two things. First of all, the covalent bonds are relatively strong. And also, there is a limited number of slip systems. So in crystalline ceramics, either ionic or covalent, the dislocation motion is more difficult. So that's why the plastic deformation is really limited for these crystalline ceramics. We also presented that some ceramics are amorphous, and so we don't have hardening of the atoms in such kind of materials. So we don't have plastic deformations that occur via dislocation movement, and we have more materials that behave like a viscous system. So the deformation, the mechanism of deformation is totally different. When we talked about ceramics, we also presented that in this kind of material, due to the way they are produced, we have a high porosity. And so this comes from the fact that many of them are prepared from powders, and this powder is compacted. And so we still have some voids between two particles of powder, even after sinterization. And so this porosity directly impacts the mechanical behavior of ceramics. So in generally, it has a negative effect. So for example, on this figure is represented the flexural strength of a ceramic as a function of the volume fraction porosity. And so when the volume fraction porosity increases, that means that the porosity rises. And so you can see that the flexural strength decreases almost exponentially with the volume fraction porosity. So this is due to two reasons. First of all, the pores reduce the cross-sectional area across which a load is applied, because of course the load is only applied to matter and so not to the void. So if we increase the number of void, if we increase the volume fraction porosity, we decrease the volume of matter, and so we decrease the cross-sectional area to which the load is applied in our sample. And also because pores act as stress concentrators. And so for these two reasons, these two effects, we have a negative effect of the porosity on mechanical properties. In this table, we present typical values for the flexural strength and the modulus of elasticity of 10 common ceramic materials. So all of them, as we presented when we talked about ceramics, have different degree of crystallinity. Some of them are glass or glass ceramics or crystalline ceramics. They have different kind of chemical bonds with different ionic degree and different crystalline systems. And these directly reflect on their properties. And something also that we just commented is that they are prepared in different way, and so we should also take into account the porosity of this material when we present such results. So for example, for magnesium oxide, here it is given that it has been sintered and the porosity is about 5%. So you can see that we have a wide range of flexural strengths, and the range of modulus of elasticity, as we presented, range between 70 to 500 gigapascal. Finally, let's talk about polymers, which is the last class of materials that we study in this lesson. For polymers, we will notice three different stress-strain behaviors that will directly depend on the molecular structure of these materials. The elastic modulus can be also determined by tensile tests, like we've done with metals, and it will range from 3 megapascal to 4 gigapascal. So the elastic modulus of this material is really lower than the one for ceramics or metals. So what are the different behaviors? First of all, let's talk about fragile polymers. So fragile polymers are brittle, so they have a high elastic modulus compared to the other polymer, and they will break right after the elastic domain, or they will withstand a low plastic deformation. So the strain at break will be low, and the stress at break will be relatively high. Then we have ductile thermoplastic polymers. So after the elastic deformation, they withstand a high plastic deformation up to break. And finally, we have elastomers. So in elastomers, let's remember the chemical structures, the chain structure. We have the chains that are amorphous, and we have cross-linking points between the chains in order to form the 3D network. And so when the load, tensile load, will be applied to this material, we will observe the alignment of the chain that have a high mobility in these conditions, and so they will align in the same direction as the load is applied, up to a certain point that the chain will be almost totally stretched, and so the crossing point will limit higher deformation. So that's why we observe when they are all aligned, so they are aligned in this region, so we relatively low load or low stress is necessary to deform and align these chains. And then when parts of this chain are being aligned, so we can observe an increase eventually of the stress if we have some crystals that are get formed and so on. But let's say that what is very typical of elastomers is that they can withstand very high deformation up to 100% in some cases. So for plastic polymers, the shape of the stress-strain curve is also very different from the one of metals. In that case, you can see the elastic region and then the yield stress, the yield point, and a decrease of the stress after this point, and in that case, an increase again of the stress up to fracture. And so in that case, the ultimate tensile strength will be taken to be where fracture will occur. So in plastic polymers, in thermoplastic polymers, we saw that we have either amorphous polymer or semi-crystalline polymers. So let's talk about these semi-crystalline polymers in order to explain what is happening, what is the mechanism of deformation, and why it results in this very special and strange shape of curve. So you may remember that in semi-crystalline polymers, we have these spherulites in which we have lamellas, and between the lamellas we have amorphous portion of the chains. And so when we begin to stretch this polymer, we have first of all the stretching of the amorphous regions that have the highest mobility. So they will be stretched, okay, and this corresponds to the elastic domain. So this is what occurs in the elastic region. After that, we will observe, we will enter into plastic deformation regime. So after that, we have orientation of the lamella in the load direction. So in that case, in this pink representation, the load is applied vertically. So the lamella orientate in the load direction. After that, we have separation of the crystallite in different blocks. So we have the breaking of these crystals. And after the orientation of the blocks and of the amorphous parts between the blocks up to fracture of the polymeric chains. And so we will observe also necking phenomena and extension of the specimen while the strain is increasing. And so for brittle polymers, we will have the fractures that will begin before orientation process. That's why we have low plastic deformation. And so since here we have orientation of the chains, breaking of the crystals, we have in fact we can imagine the importance of the secondary bonds in the tensile behavior, because the secondary bonds between the chains, if they are of high force, high energy, so it will require more load or more stress for the chain to align and for the crystal to break upon tensile stress. So that's why we say that secondary bonds govern the tensile behavior in polymers. And it is not primary bonds, because what is going to happen up to fracture is totally related to the secondary bond, and at fracture we have just the primary bonds that are covalent bonds that break in the polymeric chains. So in this table, we can see some value for the tensile modulus, tensile strength, yield strength, and elongation at break for different polymers. As you can see, depending on the class of polymer and the network structure that you have, you obtain very different mechanical behavior. So, for example, polyethylene, which is a thermoplastic, will have a tensile modulus that will be much lower than the one of bakelite, which is a thermoset, which is a resin. And the lowest example, the lowest value of tensile modulus that we can find in this table is the one of natural rubber that is cross-linked, which is an elastomer. So you can see that the elastic modulus, we confirm that it is higher for thermoset. It is a fragile polymer. Then we have the thermoplastic polymers, ductile polymers, and then the one for elastomers. Okay. Then the tensile strength of bakelite will be much higher than the one for thermoplastic. That will be higher than the one for elastomers. In that case, the value of polyethylene and natural rubber are quite similar, because we have a special effect that is occurring in natural rubber, that during the stretching of the chains, they get aligned and they can form crystals during the stretching phenomena. So that's why it is a little bit particular, but you should not remember it. It's not so important in this lesson. And so the elongation at break, the one for the resin, the fragile polymer, is very low, much lower than the one of thermoplastic. That is much lower than the one of the elastomers. So we have already commented about the elastic modulus of polymer, which is lower than the one of metal. Concerning the ultimate tensile strength, it is lower than in metal, but the strain at break is can reach very high value, specifically for elastomers. So let's now comment briefly the influence of other parameters, and for example, the effect of temperature on the tensile properties of metals in that case. So here is the example of steel. You can see that depending on the temperature at which the test was performed, the behavior of this metal changed dramatically. So at room temperature, we have the ductile material, we have the elastic domain right here, and then plastic deformation. When we decrease the temperature to minus 100 degrees C, so the elastic domain extends and the yield stress increases, the deformation at break decreases. Whereas when the temperature is lower up to minus 200 degrees C, you can see that you obtain a brittle material. And so when the temperature, let's say increases, so the plastic regime is achieved at lower stress. Okay, so here you should have a look to the transition between the elastic domain and the plastic domain. So you have a great influence on the temperature on the tensile properties of metals. But there is also the same influence for polymers. Let's have a look to this graphic, where we can see that for this polymethyl methacrylate polymer, which is an amorphous thermoplastic polymer, we have the behavior that change from a ductile polymer up to a brittle polymer. And so this is directly related to the thermal properties of polymer. So let's remember, for an amorphous thermoplastic polymer, we have the glass transition temperature. In that case, it is about 100, I think. And so when you are above 100, you have a ductile material. And when the material is used below its glass transition temperature, it becomes to be much more brittle because the chain do not have mobility anymore, and it gets worse when we decrease again the temperature up to very low temperature. So for example, in that case, 4 degrees C. Okay, so the tensile behavior of polymers is also highly related to temperature, and this should be directly compared to the thermal transition of these polymers. On the figure on the right side of this slide, there is the influence of the strain rate. So the same polymer that is stressed at the same temperature will have a different behavior depending on the strain rate. So if we use it at a relatively low strain rate, you can see that you have a ductile material, and when you increase the strain rate, it seems that the behavior tends to be more fragile. So that's why it is very important to define the strain rate and to have a look to the technical standards when you want to be able to compare your result to the result of the literature. Then we have also the influence of the atmospheric conditions. So in that case, this table gives an example of the influence of the moisture on the mechanical properties of nylon. So in the case of nylon, we have some chemical groups along the polymer backbone that are sensitive to water. And so depending on the amount of water in the polymer, so the polymer can absorb water, and depending on the amount of water it absorbed, so it directly impacts the mechanical properties. So the tensile strength decreases, the elongation at break increases, the yield strength decreases, elongation at yield also increase. So you can see that it impacts a lot the mechanical properties. So we can say that the mechanical properties of polymer are highly dependent on several factors. So we present it right here: the temperature, the speed or strain rate for the test, the atmospheric conditions, also the thermal history of material and the processing conditions, and the orientation of the chains, since we saw that for thermoplastic we have a phenomena of orientation of chains during deformation, plastic deformation, elastic and plastic deformation. And so the original orientation of the chains of the product directly impacts the shape and the behavior of the tensile behavior of the polymer. So now let's introduce the concept of viscoelasticity in polymers that enable to understand the evolution of the different mechanical properties that we can have depending on temperature and time. let's introduce the situation. Here we are going to apply a load, constant load, to the polymer at a time ta, and this load will be applied to a time tr. Then it is removed, and we are going to see the state of the polymer after the load is removed. So let's consider what is happening with the deformation of different cases. So in case B, you have the strain, the deformation of the material that is 0 up to the application of the load at TA. The strain immediately increases up to a certain value, and this value is maintained. So the deformation does not change anymore after up to the removal of the load, and the sample comes back to its initial stage or initial shape, and the strain is totally recovered. So this is what we call an elastic material. So this material is deformed in its elastic region, or it is totally elastic. Okay, then let's consider the case D. In that case, we have the material that is in its initial shape up to TA, and at TA we can see a progressive increase of the strain. It progressively increases and increases up to the removal of the stress. And in that case, at TR, we can see that the value of the deformation is the maximal value of deformation that this sample withstands. And so we are going to call this kind of material viscous materials. So the deformation is not instantaneous upon application of the load. It is progressive, and there is no recovery of deformation after the load is removed. So this is what we observed in liquids. And then we have an intermediate case, which is case C, and that is going to represent what is observed in polymers. So what is happening? At TA, we have instantaneous increase of deformation, and this deformation is rising up to TR. When the load is removed, we can see an instantaneous recovery of, we have an instantaneous recovery of deformation of the strain. And after that, it seems that the material will continue to recover slowly the deformation. So, in fact, in case C, we have an intermediate situation between case B, of a totally elastic material, and of case D, totally viscous material. And so this behavior of case C represents display both elastic and viscous behavior, and in fact it is representative of viscoelastic material and typically of polymers. So in polymers we will have the influence of the load, but also of the time during which the load is applied. And so the viscoelastic behavior of polymers is dependent on the temperature and also the time. And for thermoplastic polymers, we will have different similarity of this viscoelasticity, or it will behave more as a viscous material, or it will behave more like elastic material. And at low temperature, we will have the behavior of a more elastic material, whereas at high temperature, when and specifically when it comes above either the melting temperature of the TG of amorphous thermoplastic polymers, it will become viscous. Okay, now let's introduce another test that can be performed on materials, which is the measurement of hardness. So hardness measures a material's resistance to localized plastic deformation, which is a formation of a permanent indentation or scratch. So in that case, the stimulus that is applied to the material is a small indenter, which is forced into the surface of the material, as you can see. So the indenter in these figures is represented in blue. We apply a force in red on this indenter, and so we control this load and the rate of application of this load. And what is the response? We are going to measure the depth and the size of the resulting stamp on the material, which is related to hardness number. So depending on the characteristics, mechanical characteristics of the material, we will have different depths and size of the resulting stamp. In hard material, we won't have the penetration of the indenter in the material will be relatively low, and the diameter of the stamp will be also low. Whereas in the case of a soft material, the indenter will be able to penetrate more easily into the material, and the dimension of this stamp will be higher. So what are the advantages of hardness test in comparison to tensile tests? So this test is much more simple to perform than tensile test. We don't need to prepare specific specimen with specific dimensions and shape. And so it makes this test much more, the cost of this test is much lower than performing a tensile test. We can also test small samples, and it is non-destructive. We will only perform a small indentation on the surface of the material. And other mechanical properties can be estimated from hardness data. When the hardness increases, that means that the tensile strength of the material increases. And different tests exist. So we have different geometry of indenters, as you can see on this figure. You can see spherical diamond-tipped cone, or another one that is totally spherical. So the geometry of the indenter can vary depending on the test that we are performing. The load also can vary. The hardness range that is measured also depends. So of course, if we are working with a soft material or if we are working with a hard material, we are going to use hardness range using different hardness scale, in fact. So the measurement of hardness is relative. It is not an absolute value, as we can, as we could have in the tensile test or flexural test. And so on the right part of the slide, you can see different scales, hardness scale, that can be converted from one to another, but in fact we are more doing a comparison between this hardness scale than a real conversion of the values. And each hardness scale tell you, so we have a specific technical standards that tell you what is the dimension and the size, the dimension and the shape of the indenter, the load, etc., that should be applied in order to get the result and to be able to see if the hardness of the material is low or high on a specific hardness scale. Okay, so now you know why knowing the mechanical properties of a material is important to design a product, how to perform a tensile test, and how to identify the elastic and plastic regimes. what occurs in the elastic and plastic regimes at the microscopic scale. So when we were talking about the force of bonding, and also dislocation, and also the alignment of the polymeric chain. So that enables us to explain what is occurring in the elastic and plastic regime in each class of materials. You know the shape of the stress-strain curves of the different kinds of materials and how it is related to the chemical bond, as we commented. And also we introduced the hardness test that plastically deform the material and enable us to have some idea about the tensile strength of the materials without performing, without the necessity to prepare specific specimen and without destroying materials. So of course, in this lesson, we didn't present all the mechanical tests that can be performed on materials. There are numerous others that can be done, and depending on the application for your material, it might be more appropriate to perform other tests that were not introduced here. For example, we can name wear test, which measures the abrasion resistance of a material. Either we can also think about dynamic test, where a load is applied dynamically during various cycles in order to evaluate the fatigue resistance of a material, and so on. So thank you very much. If you have any question about what we studied, you can send me an email. Either we will have a talk on TG, you can send your question on TG, on Bate-Papo. Either you can also wait for the next session of questions that will be on Wednesday, the 13th of May at 5 p.m. Thank you very much.